Welcome to Manifold. My guest today is Tim Dettmers. If you are an AI or large language model nerd like me, you'll already be familiar with him. He's very, very well known for his work on quantization, research which is used to speed up training and inference using these large language models. He is a PhD student at the University of Washington in computer science. Tim, welcome to the podcast.
Hi, Steve. Yeah, thank you so much for having me.
Great. So as I was explaining to you before we started, I always try to start the podcast by asking just a little bit about the history of each guest so that the audience can understand them a little bit better as people. So maybe you could tell me a little bit about your childhood, how you got interested in computers, how you ended up in the United States.
Yeah. I think for me, I have a little bit of a unique story that also sort of explains a little bit why I focus on certain kind of research. And for me, what was sort of very significant in my history and my life was I'm a dyslexic. I never really did well at school. And I did so poorly that I was kicked out of school. So I didn't finish high school. It was like so bad that even at math, I couldn't do well because at some point, if you sort of go through the grades, at some point, math problems become text problems. So it becomes like an exercise of understanding the text, asking yourself a question, then do the math. And I had just difficulty with that. And so that didn't work out. And so it feels like that was a significant part sort of my early life. It was also not helping that I was growing up on the countryside. I come from like a small village. There are probably more cows and people. So people were not equipped with dyslexics and dealing with dyslexic students. And it was also not recognized that I was dyslexic. Teachers thought like I was slow. And similar to with my two brothers, they are also dyslexics. They also had issues and they have like stories on their own. But for me, that was sort of a difficult start. I didn't earn a high school degree, but somehow I still got here, and I'm doing a PhD now, sort of at the University of Washington in Seattle. And so the sort of path through that was quite unique. And well, there's sort of multiple milestones, and there was sort of a phase where I was sort of exploring. If you're kicked out of high school, you're sort of doubting yourself. A lot of teachers said like, I wouldn't amount to anything. My German teacher, so I'm German, and my German teacher told me, I think what would be best to you is to look for a job that doesn't require any mental capacity. And so that's pretty harsh. But that was sort of my reality. People just didn't really believe in me. But there was one teacher that believed in me. And I think that's a quite common story for many sort of students that grew up with a disadvantaged background. There's like one person that believes in you, and they sort of set up the path for you. And that was a teacher in computer science. And he sort of realized that there are some things where I'm maybe a little bit slow, but he also recognized that I have like some unique talent and I can really use that. And so that was quite encouraging. And so I felt like I want to do something with computers. That's maybe something I can do. And so I journeyed through sort of a couple of internships that didn't land anything. And so at some point, so in Germany, 2/3 of young people do apprenticeships. So in apprenticeships, you're like half a part-time in a company, part-time you do sort of a vocational school where you learn about your vocation. And so I tried to become a programmer. And in the beginning, it was sort of hard. And at some point, I was sort of offered an apprenticeship. And I can make a choice between like being a normal programmer or a new apprenticeship, which is sort of mathematical software developer. And I thought like, hey, I want to give this new one a try. It will be probably really difficult. And so I started with that and sort of gave it my all. And then I realized, hey, this is actually really easy. And sort of what changed was just the method of instruction. It was very practical. It was like, I got some problems and I needed to program them up. And that was a very different environment. So that was an environment I could excel at. And I did. And so, sort of, I had sort of key experience where in sort of my high school, it was every teacher assumed I wouldn't know the answer to questions. In the vocational school, it was the opposite. Every teacher thought like, "Oh, Tim knows the answer. I don't need to ask Tim, and let's take someone else." And so that was like a very sharp contrast, and that basically led me to believe that, hey, I shouldn't trust people and how they judge me. I try to evaluate myself and try to do my best. And that was also a mindset that was very important, sort of going forward. And then, yeah, I was sort of step by step, I realized, hey, I can do more. Let's try to get to university. And so I was not allowed to attend university in Germany, but I could find there's the Open University. It's actually the oldest distance for online learning university in the world. It's more than 200 years old. You could usually you get things by mail and you do your things, and then you go to a location to do actual exams, and they are sort of handwritten. And sort of my background there was I tried different things. I was interested in philosophy, then a little bit of psychology, and then sort of neuroscience. I actually studied psychology, but I still have the problem of being dyslexic. That if I write essays by with a computer, no problem at all. But the exams were handwritten, and I couldn't do it. It was too difficult. And so I already set myself the goal that I want to become a researcher, but I couldn't do that because of these handwritten exams. And so then I decided to switch to applied math because nobody cares what you write in applied math. You just need to have the correct symbols and then things are fine. And so that worked out perfectly. So I earned my degree in applied math. Then from there, I could get a degree, go to a real university. And so I went to the university in Switzerland, University of Lugano. And there I learned computer science. Um, in this process, basically, when I started, I was already very interested in neural networks and artificial intelligence. I did like Kaggle competition. I realized if you program custom neural networks and GPUs, they're just very, very powerful. And so from there, I saw like, hey, this GPUs will get better. Neural networks will become the thing. I need to do this. And sort of that is where I really put everything aside and decided to pursue this sort of long path towards a PhD to study this carefully. And so in the end, I ended up at the University of Washington. And here, yeah, I do research in efficient neural networks, large neural networks. I try to make them as accessible as possible. And so for me in this sort of story, that's sort of a very significant part is if the internet wouldn't have existed, I wouldn't be where I am now. Because I didn't have sort of the most traditional path, it was very important to learn from the internet. And I feel like language models can give something similar to people. And so for me, it's important that people have the ability to access the resources to learn, to become good at language modeling, fine tuning language models, just working with that. And so as the economy changes, that they can get the skills to participate on the highest level in the economy. And that's my goal, my research, and that's what I'm passionate about. And that's sort of the trajectory I took to get here.
It's a fascinating story, a wonderful story. Thank you for telling us that. I'm curious, just from the psychological perspective, do you feel you have particularly good insight in kind of low level processes, like in thinking about what the GPU is doing? And like, that's a special skill. Like some programmers maybe are more verbally talented and stuff, but they don't have a good sense of what's happening at the low level.
Yeah. I feel like there are certain things I'm really good at. So as a dyslexic, you're not really good at language, but it can give you some advantages. And from dyslexic person to dyslexic person is a little bit different. Um, Usually detailed processing is not the hallmark of dyslexia, but I don't know, things about efficiency, GPUs, sort of orchestrating data streams to systems and make it as efficient as possible, go through the caches, the parallelism, and that clicks and it works for me. And I feel like that was always sort of a certain interest. Like if you have a system, how can you optimize it? How does it really run smoothly? And that is sort of one area. And then the other area, and that's more common for dyslexics, sort of more this high level vision, like how can you put everything together so you can achieve a high level goal? And so for me, that is also, I guess, where I'm unique. I do sort of full stack research. I look at the lowest level things, but then I put these together so that you can have high level benefits for everyone.
Got it. No, even though you're dyslexic and maybe writing is not your strongest capability, I was very interested in your personal website because you had having been a professor for a long time. And I think I once wrote some advice to a potential grad student a long time ago that a lot of students have looked at now. I saw yours, which I thought was really thoughtful. And so you have kind of I think 3 or 4 different rubrics for the way to think about your graduate school and then later a professional career. And that, obviously different choices of which graduate program you enroll in would maybe optimize one, but not optimize
Mhm.
the other. I'm curious, like looking back, well, maybe if you feel like it, maybe you could just kind of summarize that a little bit for the listeners, but then like
Yeah,
whether you've updated your thinking on that. I could put a link
yeah,
to that essay
yeah.
in the show notes.
Yeah, yeah, I like quite writing sort of essays, and I feel like that's one of my best sort of pieces of writing that I sort of created. Yeah, and sort of how I sort of structure it. It has sort of different perspectives, and the first perspective is a very common perspective, is the very career focused perspective. And I ask the question: if I choose a graduate school, what choice maximizes my career potential? And that might be things like you want to go to a prestigious school, you want to have a prestigious advisor or a skilled advisor, and you want to have enough resources to do your job. You want to have smart people around you so you can sort of learn from them, you can collaborate with them. And that is very career focused. But a lot of people just think about this single column and then they miss out on many other things. And another thing is it's a little bit personal, but it's quite important. And that's sort of the question of who do you want to be? And you can go through life and be like the most successful person ever. But if you're like an asshole, then a lot of people will not respect you, or you will be sort of a bad example of what not to be. And so it's a little bit of like, what do you look up to? But also sort of more general life choices. Do you want to always chase deadlines? Or maybe you want to say, like, today's enough work. I want to spend time with my friends or family. And that is good for them. That's good for you. And I think part of a good life is a certain balance. And for me personally, it's important to sort of give back to the community. So work is an important part. But then everyone has to ask himself who they want to be. And I think that's an important question that's often missed. And then sort of the last part is a balance between variation and sort of depth. And so it's similar to this career perspective. If you're very career focused, you can do career, 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 but then you neglect sort of everything else in life. And so for me, important was sort of a period of breadth where I explored different areas, like I was interested in philosophy, psychology, neuroscience. But in the end, I landed in machine learning, and that was like, hey, yeah, I want to do this. But I wouldn't have found this if I wouldn't have explored. And so you want to broaden your horizon enough that you can sort of have sort of an assurance that you have a certain richness of experience so you can fully flourish. Maybe there's a unique talent or a unique experience that gives you just something really special, but you miss it if you just focus on a single thing like your career. And so it's important to broaden yourself and to a certain degree. But it can also be that you deepen yourself in a particular thing. Maybe there's a particular hobby you need to spend a little bit more time, then you're over a threshold where it just enriches your life so much that all areas benefit. So yeah, it's this balance of there are certain things really important for career, and you should be sort of think about them, but you should also not neglect of you want to become a wholesome person. What is that for you? And then broaden yourself so you don't miss out on life. You want to have those experiences that you can live a full life. I think that makes a pretty complete package.
Yeah. I thought your essay was really insightful, especially since you're still a young man. So pretty wise advice you're giving to other students.
Well, thanks.
So I think you mentioned Kaggle. I think I noticed that you said you had a very high Kaggle ranking. Was it about 10 years ago? Um,
Yeah. It was about 10 years ago. So it was very sort of interesting experience because I didn't have any sort of community where I could learn machine learning. I wasn't allowed to go to university, didn't have the resources. Then was sort of the question is, how can I learn things? And Kaggle was the perfect community. And it was also a community where I could experiment with neural networks. So I developed my own neural network framework, ran it on GPUs, and tried to really see what can you do with these things. Do they work? And yeah, for some competitions, they really worked well. And that was a big success. So yeah,
so can I
Kaggle was
ask
an important chapter. Go ahead,
if you,
sorry.
as somebody who has been thinking about and working with neural nets now for 10 years, if you look back at what you thought was possible 10 years ago, and then what actually happened during the last 10 years, could you just comment on how your thinking evolved? Or maybe you knew in 2013 we would be here today in 2023. How did it work out?
Yeah, so as I said sort of before, I studied a little bit of neuroscience. And one thing that I'm particularly interested in, well, why is humans smart? And in biology, the answer seems to be quite straightforward. We have just lots and lots of neurons, and most animals cannot afford them because they cannot meet the energy requirements. Invented fire that can pre-digest food so we can get the energy, so we can have lots of neurons. And so even then, for me, it was sort of like our neural networks are not large enough. If we have larger neural networks, we probably do better. And so I thought, like, it's just a matter of computation. It's like Jeffrey Hinton said, like something similar that we had all the recipe needed for neural networks, but our computers needed to be 1,000 times faster before they worked. And
Yes.
so the question was like, if they're another 1,000 times faster, what happens then? And for me, it was clear that we will probably get better neural networks, but the question was like, how good will they be? And yeah, I wouldn't have envisioned that it is sort of a world like today. Large language models are very impressive. If you look at ChatGPT, that just changed how people perceive large language models. And yeah, they keep improving, and that's very fascinating.
Great. So having learned a little bit about you, we can talk a little bit about your work, which is directly related to bringing these powerful neural networks to the world. And so I think maybe one of the ways you describe your own research program is improving the efficiency, more or less of
Mm-hmm.
kind of like the hardware or, well, some interface between software and hardware level, improving the efficiency for deep learning and in particular lately for large language models. And so to explain to the audience, Tim is well known for his work on something called quantization. And these models are basically neural networks which have connection strengths. So the thing that the model is trained, the model is trained on data that develops certain values for these connection strengths, which are encoded in giant matrices. And what Tim has done is found a more efficient way to, in the physics language, we would say you coarse grained the information that's inside these matrices, making it much more efficient to do calculations with these matrices. And in the field, that is now known as quantization. So in other words, so in principle, in my own brain, there could be maybe even absolutely continuous value of the connection strength between two nodes. When we do floating point or continuous numbers in a computer, we are limited in the amount of accuracy. So maybe we have 32-bit accuracy, which means we could represent the continuous value of the connection strength or the entry in the matrix using 32 bits of information. Tim has pushed down through these quantizations or coarse grainings, he has pushed down the level of data necessary to represent one of these components of the matrix down to 8 bits or even 4 bits. So it's a kind of very clever innovation that has then led to an enormous speed up in how fast the algorithm is executed or how much memory is required by the computer in order to run the model. So maybe Tim, you could start by just telling us how you got interested in this problem.
Yeah, I think the main interest there, it's sort of two passions that sort of come together. One is just a sort of efficiency. It's just very interesting to think about if data flows through the system, how do you make it more efficient? The second part is really about giving people the ability to do more work, especially the people that have the least resources. And so, if you have these large language models, if you like a big company like Google, you were able to fine tune them, you were able to run them. But if you're a student with a GPU box under your desk, it's not quite so easy. So, the main thing was also how can we enable access for sort of everyday person to these large language models so they can actually work with it. They can gather experiences. They can adapt these models to their own specification, personalize it. And then with that experience, they can learn to build things with these things. And so that was sort of the main motivations there.
So I think for listeners who are not in the AI space, maybe they have this idea that, oh, OpenAI is out there and these other billion-dollar startups and Google and Microsoft, that only they can build these enormous models with a billion connections or a trillion connections. But the truth is that thanks to the work of people like Tim, there are a lot of individual developers, almost hobbyists, can maybe buy a GPU, or maybe they don't even need a GPU. And then they can actually do things, significant things with these models at home, or maybe buying some inexpensive cloud. Um, so that's this for their listeners. That's the situation that we're in now. So there's a kind of Cambrian explosion of innovation because so many people can experiment and try to build things with these models and run the models. I wanted to ask you, Tim, did you at the beginning, because you had already worked with neural nets a lot, did you already have the feeling that the precise value of the matrix element or the connection strength wasn't that important, that it could be coarse grained a little bit without losing performance? Like what were your thoughts about that before you started experimenting with quantization?
Yeah, that was one thing that was pretty apparent from the get-go. If you look at computational science, where you do sort of physical simulations, precision is quite important. And a lot of people want to work sort of in 64-bit precision. If you have simulation of like fluids or something like that, you need to sort of approximate a function over time. If you make early errors early, then you have sort of the wrong trajectory. And so then precision becomes really important. But what we found with neural networks is if you use 32 bits, they're just fine. And then you use 16 bits and they're just fine. And then with 8 bits, you need to use a couple of tricks and then it's just fine. And now we find if you can go to 4 bits, and for some networks, that's much easier. For some networks, it's much more difficult, but then you need a couple more tricks. And so it seems they're much more robust. And sort of how to think about it is neural networks are quite redundant. So they have features which are sort of correlation detectors, and they detect like what is the correlation between what I've learned before and between the inputs. And if these correlation detectors are sort of have a high value, then they say like, oh, I've detected something. I've detected a cat or a dog in this picture. And you have lots of them in parallel. So it means that if you degrade some probabilistically, it's not like in a fluid simulation that if you're off track, that you sort of go in the wrong direction. It's like you can course correct with all these sort of different features because each has a sort of little bit different course correction. Then it averages out and is quite stable. And that's, I guess, a little bit similar with sort of the brain. A little bit of brain damage is not too difficult, not too bad, but if the entire brain region dies, you're in trouble. You can recover over time. But yeah, and I think that was sort of apparent from the get-go. But the question was, how low can you go? At some point, there's significant information loss. And then it's about thinking about clever ways to really figure out what important and what information is important, where is it stored, how to preserve that, and how to use the properties of the neural network itself to make sure it can still do its job with as little precision as possible.
I think for people who have actually done neural net training or just any kind of AI algorithm training, you have an objective function, and as you train, you're doing better and better on the objective function. you can see regions where, okay, maybe I train a little bit more and I notice the parameter values are changing because of the training, but it's not really getting that much better. And so then that suddenly leads to the intuition that like some small perturbations into the specific values are not so important for the overall performance. And so that suggests that some level of coarse graining could probably work. Um, Now you develop specific tricks. So one of the interesting things, which it might be a little bit hard to convey this on a podcast, is better maybe to look at Tim's technical presentations, which I'll link to in the show notes. But he has various clever tricks for how to encode a range of potentially continuous values most efficiently, given only 4 bits to encode it or 8 bits to encode it. And so you have some bits which are affecting an exponential component, and then other bits which are maybe the coefficient of that exponential. And so it's a kind of clever thing. I'm curious, Tim, if you step back and you say, what am I actually for a particular choice of representation of data type for representing the original floating point number? What are you actually optimizing? Is it density in the regions where there's most probability of the value being, or is it accounting properly for outliers without losing them? What are the kind of trade-offs that you have to deal with?
So in the end, it's sort of about information. If you make a simple assumption, say each bit in the neural network contains equal amount of information, then it's sort of the question, how if you compress these bits of information, can you preserve most of the information? And if you look at quantization, it's like histogram binning. So if you have a histogram, that's very similar to an integer quantization. For example, if you go from 32 bits to 4 bits, it's a histogram with 16 different bins. That's how you can sort of imagine it. If you have input distribution, all your kinds of different values. Now you quantize it to 16 different values in a histogram. That's a 4-bit integer quantization. And now the information sort of density that you preserve is approximated like how well are the bins filled in each of its histogram. You can imagine like a histogram with an outlier, and that's a big problem in neural networks at a histogram has sort of equal slices between all values. And if you have one outlier, then no values in a certain stretch, then all bins in the histogram will be empty. And then when the sort of values start, then the histogram will again have bins filled with values. And so each bin that is not filled with information or with values is lost information. So if you have a 4-bit quantization and you have sort of a histogram and you have an outlier that makes half of the bins empty, that's equivalent to a 3-bit quantization. So 1 bit less. You lose 1 bit of information. And so the entirety about sort of quantization is thinking about how to preserve information if you sort of compress it. And some of it is sort of filling these bins, but that assumes that each sort of value is equally important. But what we know is that very large values in neural networks are much more important. So if you have a small weight, it's not as important as a very large weight. That's not entirely correct, but in most cases, it's sort of a good approximation. And so that means that very, very large outliers are extremely important. They need to be preserved. And that's different from like many engineering disciplines where sort of you have a noisy process, and often an outlier means like, oh, this is just a bad value. It's like a measurement error and you throw it away. Neural network, it's not a measurement error. It means that one of these feature detectors, these correlation detectors, detected a very strong sort of feature. It really knows there's really a cat. And so you need to preserve information, otherwise it's lost. And so it means both sort of making sure that you account for all the information, but then also account for the outliers that contain most information. And both sort of these things together make a good quantization that is sort of precise.
So when you quantize, I think in some of the data types you use for the quantization, you privilege zero, right? You make sure that zero is one of the options. And so if you use that kind of data type, you then end up with sparse matrices, right? Because you have a lot of zero in the matrix. Are there if you know a priori that the matrices you're dealing with are going to be sparse, are there special libraries or algorithms that make dealing with sparse matrices faster and people starting to make use of that kind of thing?
Yeah, so sparsity is like a very interesting topic. I'm very curious about it. I did a little bit of research on it and I'm still very interested in it. It's a very hard topic because if you sort of have uniform sparsity, it's very difficult to use modern hardware to basically get sort of efficiency. So usually in modern hardware, you want to read a segment of memory, but now, if you have sparse memory, then there's some filled values, then some zero values that you don't care about, then some filled values. And it's not efficient to load sort of small segments. You need to load the entire segment. And so that makes it difficult to utilize sparsity. So I worked a bit with sparsity, a bit with quantization. Quantization is much easier if you want to utilize the hardware well. That being said, if you have the right structure, so you can structure sparsity in a certain way, it can be very efficient. So one thing that I also worked on is this mixture of experts. And sort of these models structure the sparsity by saying like, I have different blocks of experts and I say like some blocks are just zero. So I throw away the experts and I just route the information through a single expert or two experts. And this is efficient for memory because now you have large chunks of segments that are zero and very large chunks that are sort of one or represented by a value. And that is sort of a better way of dealing with sparsity. But sort of these element-wide sparsities, very difficult. We actually have a paper that we didn't publish. My co-authors were quite discouraged. We tried a lot of different sparsity techniques, the sort of uniform sparsity. We tried to sort of use very smart algorithms. None of them work. It's in the end, what only that matters was how many parameters you have. It doesn't matter how you arrange it in a certain sparsity pattern. And so sparsity is very difficult and difficult to take advantage of that.
In the computational genomics work that I've done, we often end up with sparse predictors because even though there are 3 billion base pairs in your genome, for a particular complex trait, it's a very small subset of
Mm.
those, even though the absolute number could be large, like height is controlled by about 10,000 common variants, but 10,000 out of 3 billion is really small. So the predictor is super sparse. And there are many, many ways that you can exploit that to speed up the computation in genomics. I was interested in sparsity for a long time, and I gave a talk at OpenAI, I think in 2018 or 2019, and was talking to them about, I think at the time it was like GPT-2 maybe. And
Mm.
I kept asking them, I said, well, couldn't you make this run faster if you just sparsified it? Because surely a bunch of those small values are just not doing anything, right? They're just statistical fluctuations. And I don't know to what extent they took my advice to heart, but it was an interesting conversation.
Yeah, so if you look at general sciences, sparse matrix vector multiply is an extremely important operation. Sort of
Yep.
in all kind of sciences is one of the most important operations. And neural networks, it's sort of dense matrix multiply. And you see it also in supercomputers. Most supercomputers that do sort of scientific problems, they utilize like at about 3%, something like that, because it's inefficient to do sparse matrix multiply. But then it's still much, much, much more efficient than doing a dense multiply for these problems. Deep learning is a little bit different. And so, yeah, it's very difficult to optimize. OpenAI did actually, maybe they took your advice. They did actually set some sparse attention, but that was also sort of difficult to see benefits. Often you see basically that you get a 50% efficiency in terms of computation if you do it right. But then also the performance drops by about 50%. So you are where you started basically. And it just makes the approach more complicated.
So
And
I don't know if this is a well posed question, but let's suppose you take some LLM off the shelf and you do a 4-bit quantization of it.
mhm.
What fraction of the matrix elements or connections are then set to, if you privilege zero as one of the possibilities, what fraction end up just being set to zero?
So it's more. I mean, it depends sort of what data type you use. I mean, this sort of I develop a data type that's information theoretically optimal. Then you have equal amount of zeros compared to other values.
I
But
see.
if you look, for example, at floating point quantization or integer quantization, you will have much more zeros. It's not extremely imbalanced. It's like you might maybe would have 2 to 4 times more than other values, and you can actually take advantage of that by compressing it further with something like Huffman coding. but it's sort of not a super large fraction. But this is for weights. And there are other parts of neural networks that are much, much sparser. If you scale up neural network, so neural network have nonlinear activation functions. And often these nonlinear activation functions are close to zero at a certain point. And they're sort of linear in some other points.
Hmm.
And at the points that are close to zero, almost all values are zero. And that is sort of between 97 to 99% are zero. So this is actually a regime where you can take advantage of these. But if you just look at the weights, they are not so zero heavy.
I'm going to ask you one more super nerdy question at the risk of losing some of my audience, and then we can go back to the
Mhm.
practical consequences of your work. I think you said in your talk you had some interesting result, like maybe if you have the prior that the weights or whatever the numbers are that you're trying to compress are drawn from a normal distribution,
Mhm.
there's some theoretically optimal data type which relies on that, and then you represent it in terms of some normal function. Was that correct? Is that a result?
That's correct. That's
Yeah.
correct. Yeah. So if you have the integer quantization, you have a normal distribution. How you quantize it is you make slices. So if you have 16 different values and for that you make slices with equal width. If you want to do the information theoretically optimal, you do slices with equal area. And that means each of these bins have equal amount of values in them. So the area in the normal distribution represents how many values you have, basically in this interval. And so if you slice them up in that way, each bin will have equal amount of values. And then you have this sort of thing. If you have an incoming random number from the normal distribution, and you're going to predict in which bin it will land, you cannot do better than chance because
Hmm.
each bin is equally likely.
Right.
And that's information theoretically optimal.
I see. So if you have some information about about the distribution you're drawing from, then you can optimize things kind of perfectly if the prior is correct.
Yes. There's one thing is you can basically weigh each value equally, an equal amount. But we know that larger values in neural networks, they are sort of just more substantial. So you actually want to allocate more bits for
Yes.
larger values. It's a little bit like Huffman coding is information theoretically optimal, but it's not the best compression techniques. There are better compression techniques that are not information theoretically optimal, but they encounter sort of for different patterns. And yeah, it's a similar
Interesting.
principle.
Okay, so let's switch gears to practical stuff. So let's start with inference. So for the
Mhm.
audience, it means someone else maybe trained a model and gave it to you, but now you're using it. You're using it to generate results that your customer needs, and so you're running the model, and Tim has all kinds of results on someone else trained the model. Maybe they used very expensive 32-bit floating point numbers to train it. I get it. I want to, in a sense, kind of shrink it down so I can run it on cheaper hardware or very fast. And he's got results going all the way down to 8-bit or 4-bit inference. Talk a little bit about the speed up. So there's an advantage in the RAM requirements and also in the actual speed of.
Mhm. So yeah, the RAM requirement is just quite important if you want to use the largest models that are currently out there. So a couple of days ago, Llama 2 was released, which is a very powerful open source model. If you want to use the largest model available on consumer GPUs, you will need 5 consumer GPUs. And so if you have a standard consumer setup, uh, between 2 and 3 GPUs will fit there. If you have sort of custom extenders, you can fit 4 GPUs, but you cannot use 5. So it's impossible to run the consumer setup in the normal setting. So if you want to run it, you need to quantize it. It's just a requirement. You need to compress it down in some way. Quantization is the most effective way where you can preserve the performance, but make it smaller. And so you need to run it at least in 8-bit on a consumer setup. But if you run 4-bit, you can actually fit it on 2 consumer GPUs. And it's a pretty expensive setup still, but it's a doable setup. So if you're hobbyist, you can actually use the best model available out there right now with 4-bit quantization. And so that's one contribution. And then the other is sort of how fast can you go? And they are
Hey,
really go ahead.
quick question. So in that example, is the cost down to like 5K for those two consumer GPUs? You build a
Yeah,
rig at home, you spend 5K. Those are GPUs that are mainly, I guess, in the maybe pre crypto era, it was mainly gamers who are using these GPUs, right?
yep,
So, but
that's right.
they're like $1,000 or a couple $1,000, and then you can run Llama 2 fairly efficiently
Mhm.
with that setup. Okay.
Yeah. With 4-bit, it's also more efficient. So in this setting, it costs about $5,000. Um, if you buy sort of the previous generation, I think you can get it down to like 4,000. But these GPUs that have a little bit higher memory, you need 24 gigabytes, are quite in demand. Even after the crypto bust, so to speak, now a lot of AI people want it, and GPUs are sort of valuables. And so even used old GPUs are quite expensive. So you need at least 4,000 to run the largest model, but you can do it. And then sort of the speed up, there are different settings, but if you have sort of this consumer setting, you will be able to get about 8 tokens per second at the moment. And if there's some software updates, you might be even able to get a little bit higher sort of speed. And this is for a setting where you have a single prediction, a single generation. So you ask the language model, for example, a question, and it generates a response word by word. And you get basically about 8 words per second right now. That is one part of inference, and that's mostly dependent on how large the memory footprint is of the model. So if you have a 16-bit model, then you only generate at a fourth of the speed. So it might be about 2 tokens, 2 words per second. So
Mhm.
it's much slower. So you make it able to fit on consumer devices, but also make it faster. There's also a different world, which is sort of a little bit more, that's sort of in companies where you have lots and lots of queries at the same time. Then memory becomes less efficient and there are other bottlenecks. But yeah, that's a little bit different topic. Happy to go into detail also there if everything curious, but yeah.
So a question that I'm sure the people who invest in stocks, who listen to the podcast will want me to ask you is, currently NVIDIA is valued at, order $1 trillion on the assumption that I mean, of course, there'll be a lot of demand for is it A100 is the latest and greatest, or H100?
H100,
A100.
yes.
Yeah. So tremendous demand for sure for model training,
Yeah.
but maybe even bigger demand for those devices for model inference if at scale people start really using the AI for useful purposes.
Mhm.
Do you think the people that are investing fully understand the consequences of your results? Like, are you kind of thinking like those guys are overestimating because they're not taking into account the efficient quantization?
So I think there are a couple of issues. One is with the quantization. I mean, as I said, so hardware is very complex. It is optimized across very different sort of axes. And one important axis is training. If you have inference for a single person, the only thing that you need is high memory bandwidth throughput. And if you look at AMD GPUs, they give you very high value for that. You don't need expensive tensor cores and all the magic that goes with it. You just need a cheap GPU that can have sort of very high memory bandwidth. Sort of software is another sort of issue. You might have the right hardware, but then you also need to be able to use it with all the software support, with all the community support. It's sort of a little bit different issue. But with sort of using models on a personal level or even on your phone or your personal laptop, and that doesn't have such strict hardware requirements. So you will see a lot of different hardware where you can run it very efficiently. And NVIDIA doesn't have the largest benefit there. Like a lot of companies will be just as fine as NVIDIA. The only advantage right now is that sort of software support is a little bit better, community support is a little bit better, but AMD is pretty well supported, AMD GPUs. Apple Silicon gets better and better support, and you have lots of users. And so that will be very interesting. I think iPhones soon, they will run language models. It will be quite common. and it's pretty good hardware. And so all of that, like NVIDIA doesn't have the biggest advantage for inference. It's mostly training, then sort of software and community support. But yeah, other people have no drawback really. Other companies.
Yeah, that's interesting. So I think if I talk to the modal hedge fund guy who's really bullish on NVIDIA, I think what you just said is probably not incorporated into their thinking. So it would be interesting to go back now and look at their analyst reports for the projected sales of these H100s. You know, how much of that is supposed to be for inference versus model training? And probably they're incorporating a lot of inference, usage in the future as well. So that's interesting. So let's switch and talk about model training. So you have a paper on something called QLoRA.
Mhm.
LoRa stands for low rank adaptation.
Mhm.
My way of thinking about it is you have a neural net with billions of connections, but you insert some low rank objects in there, which can modify, in a sense, some of those matrices. And training just the components of those low rank matrices is relatively inexpensive. And yet, I guess some researchers have found that you can adapt your originally trained LLM quite effectively using these low rank modifiers. And so what your paper does is study LoRa, but using quantized, I guess you quantize both the original model and the low rank matrices, or I guess you're quantizing everything. Is that right?
So for the purpose of training or fine tuning, we just quantize the base model because that's very, very expensive. Though
See,
lowering adapters, so to ensure training stability, are still in higher precision.
okay. And what you found is that, again, fairly aggressive quantization still allows for good results. Is that right?
That's correct. Yeah. So the hallmark is always if you can replicate the full precision or 16-bit precision performance, and then like probably it works in most cases, and you can just apply it and it will be fine. If you have some small degradation, it often means that okay, I have a degradation here. How much degradation do I get with other tasks? So if you get the full performance, often very good signal that it just works. And it seems to just work. We tried it across like 1,000 different experiments, different data sets, different models. We always get the same results. So this technique is about 17 times more efficient in terms of memory. So you can take a big model like Llama 2. And as I said, now we have a $4,000 setup or $5,000 setup. And now you can actually personalize it. You can take the model, fine tune it on your data, and you can do very interesting, curious things. You can build chatbot models that sort of mimic a person, that mimic a podcast, a conversation. And you can have all kinds of different things. Your imagination is the limit. And so, yeah, this enables really not only the usage, but the sort of personalization of models. And you can do it on your own consumer hardware.
And have you done any research at all on the actual training of foundation models after quantization?
Yeah, so I'm quite curious, as I said, about sparsity. And sort of for about a year, I was like very interested in a mixture of experts. I still am, and it's just a mixture of experts. There was sort of the question: how do you train well with them? So again, mixture of experts is a setup where you have a neural network, and parts of the neural networks are shared, or you also have completely separate neural networks. Now you want to route information to experts. So you have generalist layer and expert layers. And if you have, so let's say 100 experts, but you only route to 2 experts, you save 50% of your computation. And so that can make training much cheaper. And so that research was really about how to do it more effectively. The research that I did didn't quite pan out, but I worked with some colleagues and on mix of experts approaches. And we have like 2 different approaches that we published. One is base layers, and there you actually use optimal transport, the synchron algorithm. That sort of also models heat flow. And we basically model, if you think about it, sort of the information flow, how you route different words to different experts. And so certain experts are sort of better at certain words, but there's also contention. There might be some experts that want to get all the words, but you need to distribute it sort of equally. And sort of, if you use that algorithm, it distributes the words efficiently. And with that, you get sort of very efficient pre-training. The other sort of approaches where we have fully disconnected training, it's more training like an ensemble, where you do a little bit of pre-training in a shared model. Then you branch out into, and you feed each branch, you treat it as an expert. And each expert gets its own data set that is a little bit different than other data sets. And now these experts specialize, but because you have a sort of shared representation that you start with, they're still close enough in optimization space that you can actually combine them. So now you can do inference and combine certain experts if you have certain data sets. And that works really well. It's more efficient than the regular transformer. And then the last part that I worked on was sort of globally distributed training. So data centers are really, really expensive. A big part is you need to have all these GPUs and computers, but then you also need to have the networking between everything. The networking can be extremely expensive. You need to have like lots of big power sources and special building, very expensive. So what if you can take lots of consumers with their consumer GPUs under the desktops, now parallelize it to train a very large neural network? And there the problem is your network is not really fast. You have like normal Ethernet. And so that research was really about how can we compress information and structure the training so we need very little communication. The communication is very efficient and the communications overlap with computation. So the latency is hidden. You can always compute on your GPUs. And that's called swarm parallelism. That is also very effective. And so these are the works that I did in pre-training.
Do you think we'll actually see that? Do you think we'll see state of the art quality foundation models that are trained through kind of crowdsourced home resources? Is that already happening? And maybe I'm behind the times.
So it's currently not. It's like there's a company called Together, and they have sort of a similar approach. As I understand it, they use a lot of sort of compute that's currently not used at universities. And then they sort of come together and they build sort of some things for their own, but they say also to the universities, hey, we have this efficient infrastructure. If you want to train a big model, you can now use the resources across all universities to train this bigger model. And so the problem with these approaches is, and the approaches are only as good as many people you can get to sort of collaborate. And it's a collaboration problem in a sense. And so if you have large institutions like universities, that's more feasible. But with sort of consumers, it's sort of a rich get richer problem. You need to get a jump started to really get it going. But once it is going, you can imagine training models like GPT-4 on globally distributed networks. Some people, particularly in the AI safety community, they find that scary. Like, hey, now people can train powerful models that might be quite dangerous. And so it's sort of, a double-edged sword.
In this system, not only are you using Ethernet, but you're actually using the internet actually to transfer across nodes, right? And
that's right.
So is it because you have very efficient ways to compress things and then you send them? So that's really interesting.
Yeah, there's sort of a couple of innovation. One is sort of compression and quantization again. And the other is sort of the algorithm itself. The internet is noisy. You have disconnects, you have lag. Some connections might be slower. They may fast 1 second, they're slow the next second. You need to take account of that. Some computer might have a bug, or it overheats and it's very hot and needs to sort of throttle everything. Or somebody is downloading something in the network like next door. And so you need to account for all of that. And we solve this by sort of stochasticity. So you have a very stochastic, if something sort of drops, the probability is adjusted over time. And so this works really well that stochastically everything is sort of annealed to the right distribution, the right networking, and then everything is adjusted by itself. So it's compression, the stochasticity, that's sort of adjusted over itself. But then the last piece is sort of developing algorithms where you overlap computation and computation. And it's we use an approach where we send out all the updates, but then we already start the next sort of training batch. And so once update date comes in, we sort of calculate the update. And once the first computation that currently is running finishes, we do the update. Then we sort of compute the next update. That means we have a stale update on the weights. It's delayed by one step, but that allows us to overlap everything. And so we did experiments on this, and it seems that you have a delay of a single step. That's just fine. You can just train fine. Again, it's this sort of phenomenon that if you have a little bit noise, it's fine. If you have lots of noise, things break down. You cannot go to 1-bit quantization, very difficult. But 4-bit or 8-bit works. And similarly, if you have a little bit of noise in the update, that's just fine. Neural networks can deal with it. And we exploit that.
Wow. So is it possible that if they shut down the crypto Ponzi scheme, then all the mining rigs that are around could actually be reused, repurposed for this kind of algorithm?
So theoretically, yes. And the other thing, and that's sort of a little bit more hardware specific thing, the crypto rigs usually have lots and lots of GPUs. And if you have sort of an entire GPU system, there's certain bottlenecks. And actually, when I now think about it, the bottleneck is still just the internet, just still Ethernet. So actually, mining rigs should be just fine. You just need to configure them in the right way, and you should be able to, do updates just fine with this sort of parallelism.
Wow, very interesting. So after the Securities Exchange Commission clamps down on a lot of these guys, there might be a lot of spare capacity for what you want to do.
Yeah, I guess it's sort of a little bit of a meme that all the crypto bros are now the AI bros.
Yes.
But so this would be another level. They need to really come together as a community to train something within a special algorithm, special software. Theoretically possible, but in the end, it's a coordination problem.
Great. So let me, we're coming to an hour. So I just want to do maybe 2 more things and then I'll let you go. I don't want to use up too much of your time. One of my questions is, what is your baseline projection for what we're going to see in, say, on a 3-year timescale, on a 5-year timescale?
Yeah.
Any thoughts?
Yes, 3 years and 5 years. That's quite some time in AI. Everything's moving so fast. But what I can say is that what I'm seeing is the neural networks get good enough that you can do stuff with them, but they are also not good enough that they're so reliable that you can deploy them. And you get very sort of annoying user experiences, and people don't like it. Hallucinations is a big problem. And so there's some challenges. But when I look at it and sort of I orient myself quite a bit at, so there are scaling laws which project which variables are important as you scale certain dimensions. And so there are scaling laws for fine tuning, which means you use a big model. Now you fine tune it on a specialized data set. Then you can predict how well it does. And if you play around with these equations, it seems to indicate that we are in a regime where fine tuning is very powerful. So what you want to do is take a very large model and now specialize it to a very narrow task. And then it does quite well in this narrow task, maybe so well that people are actually not annoyed by their performance. Maybe it doesn't hallucinate as much. And there are other things like information retrieval that can help with that. But when I look at the future, what I see is what you will have is one base model, probably quantized and very efficient, but then lots of different adapters that are specialized for very particular use cases. And what will happen is you get particular inputs, and to ensure reliability, it's routed to the expert, to the adapter that can solve this task within a sort of boundary of specification that is good enough to ensure good experience, good user experience, or a sort of a good code generation. It can solve a subtask in enough quality where you can say, this is good enough that we don't need a human in the loop, or that we don't need manual fine tuning. As soon as you introduce manual sort of fine tuning, it's not very efficient. And so when I look at that, I think that is sort of what the future will be. I think that will become very rapidly the future. If I look in 3 to 5 years, another thing that I see is hardware doesn't get much better anymore. It's very difficult to get improvements. You can still get improvements by just using more GPUs, and that is still feasible. And if you have efficient algorithm like swarm parallelism that I discussed, you can have larger and larger sort of clusters. So I could imagine that Google and OpenAI will use a million GPUs in the future, but it will reach physical limits. You can only exchange information at the speed of light, and that that is the limit. So, and if our GPUs don't get faster, we are soon will be bottlenecked by networking. So a question will be like, in 3 to 5 years, will we hit models that are sort of good enough to solve the problems that really matter to make AI efficient? If you look at the productivity paradox in computing, is like computers didn't improve productivity in the beginning. So a lot of small pieces that needed to come together to sort of optimize the
Yes.
entire process, the entire pipeline. And so um, that will be the curious question. So I think a big focus will be on reliability. Can you get these models to do a narrow task very well that is still valuable enough so we really want to automate with AI? But then also, do our AI models get good enough so we can actually use them well? And I think we will know that answer probably in 3 to 5 years. I think physical limits is a little bit further out, but it's not that much out. So I think in 10 years, we probably hit physical limits, and then we have what we have. Yeah, that's how I see it.
Well, Tim, I like your answer because this idea of like trying to build narrower AIs that using fine tuning and information retrieval can actually do narrow, economically valuable tasks. That's a thesis of our startup. So
Mm,
you're kind of thinking along the same lines that we are actually for what we think the next big impact will be from AI. So I like that. I noticed you didn't say anything about AGI. So some people who are really either doomers or I would say very optimistic about the rate of technology advancement would say, oh, 3 to 5 years, Steve, by that time we'll already hit AGI. And it sounds like you don't think that's very plausible.
yeah. So I mean, I'm a fan again, sort of neuroscience. If you compare different animals, yes, sort of the different sort of orders of magnitude of improvement between like sort of dumb animals, smart animals, than humans. And humans just have lots and lots of computational power. It's just unparalleled. It's not comparable to all the supercomputers that we have today. Single brain is
Yes.
much more powerful still. And if I look at hardware, it will not improve much anymore. And so if I put these together, then we will not reach sort of human level capability processing power. And then the question becomes, can you get a very intelligent system with less computational resources than a human brain? And I think if I look at sort of AI, it uses backpropagation, which the brain cannot use, and it is more efficient. And so we might be able to get there. But what I also see is that GPT-4 was very expensive. It's still very flawed. It's very good at sort of things that you don't know about. But if you ask it sort of narrow expert question, it gets lost. It doesn't know what it's doing. And you have sort of this last mile problem that you have in self-driving cars. You have a similar problem with AI. And so I think what we will see is very powerful AI tools that can do a lot of tasks much better than humans, but at some tasks they will just not reach our capability. And this will be very powerful, but it will not be AGI. They will not be able to do everything as good as we do. Humans are amazing, and I don't think we quite get there.
Yeah, it's funny because you and I didn't, to the audience, Tim and I did not coordinate on this or anything, but my view is very similar. In 3 to 5 years, we'll see narrow applications where the AI is clearly superhuman in that narrow domain, but we won't see superhuman generalist AIs yet in 3 to 5 years. Beyond that, it's a little hard for me to speculate. But so Tim, seems like Tim and I are kind of roughly the same in our calibration. Great. So any last thing? So anything I didn't ask you about that you think is super important for people interested in AI to understand? We could just take the last few minutes for that.
Let me see. I think we touched a lot of different points, and sort of was very broad. Yeah, there's nothing in particular. Maybe one thing, and that's sort of what I see. I'm PhD students. I work in academia. And there's sort of often this feeling of being lost. There are these large companies and they have these big models, and they cost hundreds of millions of dollars. And people feel like, oh, I can't do that. I don't have the skills. But from my personal experience throughout life, and also what I see now in technology is we can use these models. We can personalize them. We don't need to fine tune, train the entire sort of models that cost $100 million, but you can experiment with them. If you have $4,000, you have a computer you can use for years to experiment with these. And it's very cheap, even if you use the cloud. You can do like a very interesting experiments with like $100 or so. So it's not inaccessible. It opened up. It's sort of the Cambrian explosion, as Steve said. It opens up so many possibilities, and people are not quite aware of it. Some people are very pessimistic. I'm very optimistic. I think we can do so much more than we could do a couple of years ago, and that's very exciting.
I agree with you 100%. I think people will be surprised at how much innovation comes from the grassroots level and not from the mega corporation. And I want to thank you, Tim Dettmers, for helping to make that a reality.
Yeah, thank you so much, Steve.
Great. Well, it's been great having you, and maybe we can have you again sometime in the future.
Yeah, I would love that.